Я выигрываю.
Короче, кстати, в отличие от рынка, отвечает на физику. То есть он когда отвечает, он хотя бы делает то, что я не сказал, и проверит свой закон. Он проверил. Я рынку написал, что меня не проставлю.
И что, заработало? Да. Ой, спасибо. Спасибо большое. Ага. Okay. So sorry about this. So we were deducing this simple corollary from this lemma that all the fibers of finite morphism are finite, and if not, then there would be not a point irreducible component in the fiber. So it contains some point, but is strictly bigger. But then it immediately contradicts because the image of this component coincides with the image of this point. Yeah. Okay, so
How used that the image is infinite?
If it is infinite, it cannot be just a disjoint union of infinitely many points, because this is not an algebraic variety. So
it must be a variety
because the fiber, yeah, infinitely many points, but disjoint union. Is not an algebraic variety. Okay, so now let's prove this lemma. So again, the statement is local over y. So we can assume that y is y is affine. Moreover, we don't need the whole of x. We can assume that x is this bigger component z2. And then it contains strictly smaller, irreducible, closed subvariety z. Okay, and then again we want. So we want to prove then. Moreover, we can also assume that y equals pi of z. Yeah, just you can replace y by the image of pi of x. Sorry, pi of x. So y is surjective. Okay, so pardon me. We can replace y by the image of pi of x. It's a closed subvariety of y, so it's also affine. We lose nothing. So we have to prove that the image of this smaller component above is strictly smaller than the whole of y. Okay. In other words, we want to produce a function on y which vanishes here. A regular function say g in a regular function on y such that g of z is 0, but g is not identically 0. Okay.
Not on z, but on p.
Oh, right. Pi of z, yes. Okay, but what we do know is that there is a similar function above. Yeah. So there is a function on x such that f of z is 0, but f is not identically 0. Okay, but now we know that x is finite over y, and this means that f satisfies a polynomial equation. Yeah, it's an integral element. So k of x is finite over k of y. And if we take f squared, f cubed, and so on, they cannot be all independent. So there is some dependency, namely the sum of f to the power I from I equals 0 to, say, d minus 1 equals f to the power d. Okay, from some point on, we can express this power from the previous ones. Oh, sorry, that's not quite so. There's AI. Okay, and AI, they are functions on y. And we can assume that the lowest coefficient is not 0, right? Otherwise, we can just cancel out some power of f. A0 is not 0. Okay, and then we can rewrite just passing everything else to the right hand side, that A0 is what? F to the power d minus the sum from I equals 1 to d minus 1 AI f to the power I. And in other words, it means that A0 is divisible by f, right? Because you can, well, everything here is divisible by f in the right hand side, right? I mean, in functions on x. Okay, and this means that A0 restricted to z is 0. Okay, and there we are, because A0 is lifted from y. It means that A0 vanishes on the image of z. But A0 was not identically 0. Right?
Ты мне очень хорошо говоришь, что А0 ограничено на z, потому что А0, оно все-таки в k от y, нет?
But yes, but k of y lies inside k of x, right? It is subalgebra.
Okay.
So the lemma is proved. Okay, and now we move to our next big topic. That is the topic of dimension. Because, well, we all do have some intuitive notion of dimension. For example, we're speaking of curves, yeah, and the affine space AN is supposed to have dimension n, but what does it mean exactly? So in what sense this has dimension 1? Now with this Zariski topology, the definition is very simple. I know if you studied some analysis, then probably have heard of Hausdorff dimension. It can be any number at all, so the usual notion of dimension is pretty advanced. But in this case, it's very simple-minded. So we say that a dimension of algebraic variety x equals n if there is a chain of irreducible closed subvarieties zi in x, namely z0 inside z1 inside zn that is equal to x, and these are all strict embeddings. Okay, no other chain has length bigger than n. Okay, so the longest possible chain like this has length n. This is dimension n. So far we only know that the dimension of a point is 0. That's for sure. So we don't even know the dimension of the affine space is its number, so to say. But let's prove this. So we'll start with the following lemma. That again we have a finite morphism. And then dimension of x equals dimension of y. This will allow us to compute dimensions. Pardon me?
Finite surjective morphism.
Oh, right. Finite surjective, yes, thank you. So somehow intuitively the dimension of y should be smaller than dimension of x, right? But formally it's easier to prove the opposite inequality. So the first part is that the dimension of y is at least dimension of x. And how do we prove this? Well, we take a chain like this. Yeah. So we apply pi of z0 inside pi of z1 inside so on. But by the previous lemma, these are all strict embeddings. Okay, but now we have to prove the opposite inequality. And this not difficult either. So do you have any suggestions? So let's start from say W0 and so on. And let's So what do? We consider its pre-image, and what do?
Pre-image of closed is closed.
Absolutely, yes. So but unfortunately, it can be reducible. Yeah. Any examples? By definition, it's a continuous morphism. But so, how can it be reducible? Any examples? Yeah. For example, so pre-image can consist of 2 points. Yeah, this is what you meant, right? Or also you can consider morphism from A2 to A1, where x and y goes to the product xy, and then the typical image will be sort of hyperbola, but the zero level will be just two lines, so reducible. Okay, so it's not very good, but still it's not bad either, because we can just take one reducible component. Then certainly we have to take some care, because if we choose them randomly for arbitrary wi's, then they will be not embedded into each other. But let's proceed, say, from top or from bottom, whatever. Take some care, say, going up in I or down in I, and get a chain in X. Okay, there we are, and now we're in a, pardon me?
Если мы взяли так, что в каком-то W там непереводимый компонент такая же, как W следующий. Нужно что сказать про то, что у нас
there cannot be equal, yeah. But this would contradict this famous previous lemma.
Why can coincide two components of these spaces?
Well, we can just by this lemma, which used to be at this blackboard,
yes.
We cannot have pi.
If they will go to different things, maybe.
Ну, в качестве них образа при взятии непереводимой компоненты образ остается такой же.
Yeah. So can be reducible, but take one reducible component such that pi of zi equals wi.
Well, why such exists?
I mean, the whole thing covers. Yeah, this pi was surjective, so the pi of pi inverse of wi is wi. That's for sure.
Yeah.
So one of irreducible components of this pre-image does cover the whole. I mean, the image of anything is closed. So this is the union of few closed subvarieties, but it's irreducible. So it must coincide with some of them, just by definition of reducibility.
So we take an example. We take an image of all different closed things.
Yes.
Which is given this position.
Okay, so the next claim is finally that the dimension of the affine space AN is exactly n. So we have to start with some chain. So which chain would you propose?
Point and line in plane.
Right, all right. So I have 0 in A1, in A2, and so on in AN is length M chain. That's fine. But now I have to prove that there is no longer chain. Yeah. So suppose there is a chain of length say p strictly bigger than n. Okay, then it has z p minus 1 irreducible subvariety in AN. Okay, and so it is not equal to AN. So there is a function that vanishes on this zp minus 1. So there is f which is not 0, and f restricted to zp minus 1 is 0. So in other words, zp minus 1 is a closed subvariety in the 0 set of f. Yeah, so, or the ideal generated by f. Now, this 0 set of f is at least morally n minus 1 dimensional, and we do know something about it. Namely, there was this basic Emmy-Noether lemma. ZF is finite over a n minus 1, right? Remember? Yeah, everybody agrees. And hence, dimension of ZF equals dimension an minus 1, but this equals n minus 1 by induction. And the dimension of zp minus 1 is at most dimension of zf. Yes?
Zf is finite, so its embedding is finite morphism. Do you use something like this?
I mean, this zf projects onto a n minus 1, this is finite. And we had a lemma also somewhere here that if I have a finite surjective morphism, then the dimensions coincide. Okay. And this dimension we can assume equal to n minus 1 by induction. So there we are. All right. Okay. And also well, let me just stress that we, along the way, we proved also that the 0 set of any function, so if, say, f is not a constant, then the dimension of the hypersurface ZF is inside AN. This dimension is n minus 1. Okay? I mean, we had this inequality, but now we know the dimension of AN exactly n, so the dimension of any hypersurface is exactly n minus 1. Okay. And a useful corollary is that any algebraic variety X has a finite dimension. And the proof is evidence. So if X is affine, then X lies in some affine space, and so its dimension is small. I mean, it's closed. And then its dimension is not more than n. And any algebraic variety is covered by finitely many open ones. That are affine, so they have finite dimension, and then it's immediate to check that the dimension of X is the maximum among those dimensions. Okay. Okay, so now let's study in more detail such hypersurfaces. In an affine space. Z equals Z F in AN is called a hypersurface. And some big goal we're aiming at is that so eventually, maybe even today, we'll prove that any closed dimension n-1 subvariety of An is such a hypersurface.
A union of two.
It can be a union of two, then the F union Zj is the Fj, Fg. Sorry. Okay.
Should be reducible.
Huh?
Well, we can take the union of a hypersurface and the point.
Ah, sorry. Yeah, that's true. Yeah. That any closed subvariety, maybe I should say it this way, closed subvariety with any irreducible component of dimension n-1. Yeah, you're absolutely right. Thank you. For example, in the plane, you could take the union of a line and the point. It is joint union. But then, well, it's an algebraic variety, a legitimate one, but its dimension certainly is 1, but it's certainly not a zero divisor of any function. So I should somehow prohibit such things. Yeah, thank you once again. So let's move towards this. Let's start with the proposition. Let's take a function f that is the product of powers of some irreducible polynomials. Fi to the power ni. So fi irreducible polynomial okay, and then first the irreducible components of ZF are ZFI and the ring of regular functions on ZF is the ring of polynomials modulo we would like to write just f, but it's not quite so. Yeah, we should take the radical of this ideal, so just the product of fi in the first powers. Okay, and finally each component, irreducible component of ZF has dimension -1. And if or maybe the last point is that if any irreducible component of Z has dimension n-1, then there is f such that Z equals ZF. Okay, so let's prove this proposition. Well, it's the first point is sort of a tautology. Yeah, that we know that on the one hand, ZF is the union of ZFI. Yeah, just because this ideal is a product of some powers of these ideals, and then by the Hilbert-Nullstellensatz, it doesn't matter if we take some power of those FIs. So what do we have to check? What do we have to check? That probably that that they're all distinct, for example. Yeah, because if the Fi lies inside the Fj. Oh, sorry, this is J, and this is I, and I is not J. And here also is J. Okay. Then we know that Fj restricted to the Fi is 0, right? And this means that by Hilbert-Nullstellensatz that Fj to some power capital N lies in Fi, the ideal generated by Fi, but they're all irreducible. So all Fi irreducible, and the polynomial ring is a unique factorization domain. So this implies that Fj equals Fi. And by the way, does everybody remember that the polynomial ring is a unique factorization domain? And maybe also we can open some window, no? Or otherwise I'll fall asleep right away. Yeah, so everybody remembers, and the proof is based on what?
On if you add one variable, then.
And how is it called? This step. This induction step is called Gauss lemma, right? Yeah, the proof is based on Gauss lemma about contents of polynomials. Yeah. Okay. So I think the point 1 is clear. Point 2 is also clear, I think. Point 3. Point 3. So Fi irreducible means that the ideal Fi is prime, and this means that the Fi irreducible. Okay. And has dimension n-1 is the previous claim, yeah? Okay. Yes.
Number 2 is.
Yes.
How would we see it?
Just because this is a closed subvariety, so it is given by some ideals of function, some ideal of functions vanishing on it, right? Now I claim that the ideal of functions vanishing on it is exactly this ideal.
It's the radical of.
Yeah, it's the radical of this principal ideal. This principal ideal is the radical of that principal ideal.
And by the way, we claim that dimension of GFI is equal to n-1 because of Noether lemma.
Pardon me?
We say that a dimension of
yes, yeah, by Noether lemma, yes. Okay, so we are left with 0.4. So we take a function that vanishes on Z. Maybe some other function G. G is not 0, and hence Z lies in the 0 set of this function, and now we know that this has dimension n-1, and it's the union of finitely many components Z Gi to some E. Okay, and they also all of them have the same dimension n-1, and this means that this Z is just the union of some of those irreducible components. Z G. Well, but then the corresponding function f will be the product of those G i's over this subset. Yes. Because we know that Z is equidimensional, so any component has dimension n-1. On the other hand, this bigger thing is the union of n-1 dimensional components. So necessarily this must be a union of some of those components. Then it will have smaller dimension. Yeah. So Z is a union of n-1 dimensional components, and this is also the union of n-1 dimensional components. Just take some of them. Okay, so this is proved. Okay. And this is a rather strong claim that we proved. For example, it's usually not true. I mean, for the ambient variety different from the affine space, like if I take something like this, and inside we take something of codimension 1, then there is usually it is not the divisor of some function. So in general, if x is affine, Z in x codimension 1, then there is no such a function f such that the zero divisor of f is exactly Z. Okay, we will see some examples, but in this respect, the affine space is very, very special. So A. No, even if it's affine, but not the affine space.
Is
Okay.
it true for projective space?
Pardon me?
Is it true for projective space?
Yeah, it's somehow harder to formulate. You mean there will be some homogeneous function? Yeah, this is true. Yeah, this is also true in a sense for this very reason. Yeah, but in general, it's not true. Okay. So what we also proved during this argument is that given a function on the affine space such that the dimension of ZF is smaller than n-1, we can conclude that F is invertible, yeah?
Excuse me.
Yes.
And Z is not closed in this case, Z is on the board. Because closed Z are Z with
How do you mean?
Or not.
Pardon me?
Z with head.
I mean closed, yeah, certainly closed. But not any closed subset is necessarily given by some unique global equation.
Because what is closed subset by definition, not a subset of form ZF in affine space.
No, it is given by some equations, but not necessarily by one. We'll see some examples.
We cannot multiply them by. No.
Yeah. And so it's invertible. And I expect you know what are the invertible functions on the affine space? Yeah, only constants, yeah. Because this is a polynomial, yeah? And any non-constant polynomial by the fundamental theorem of algebra does have some zeros. Invertible. This multiplicative subgroup of invertible functions. Okay. Okay. And now I hope we'll prove the main theorem today, that if X is an affine irreducible, maybe not even necessarily affine, an irreducible algebraic variety, and F a regular function on X, and we then have that any irreducible component of the zero set has dimension exactly n-1, where n is dimension of X. Okay, so that's what we know for the affine space, and it's true for any algebraic variety as well. Okay, so that just one equation cuts out the zero divisor, which has dimension exactly one less. Okay.
or empty set. If F is constant.
I don't know. This is some deep logical question, and I'm lost with it because I don't know what to say about the irreducible components of an empty set. I just don't know. Don't ask me.
This theorem is something silly because a lot of algebraic which we can try to describe, they are compact. As they are compact, their ring is K.
And so what?
It means that F is constant. Compact X.
Yeah. But still, I think this formulation is fine. You may reduce to affine varieties, and that's what we do from the very beginning. Let's prove it, and we start with lemma. And the lemma says that if X is affine, then yeah. Then this corollary holds true. So given given a regular function, but it's affine and irreducible. So given a regular function such that the dimension of the zero set is less than dimension x minus 1, then this function is invertible. So the zero set is empty. Okay. And we will prove it by reducing to this very corollary. So we know that by the M.Noether lemma there is a finite morphism pi. Surjective. Okay, so here n is dimension of x. Okay, and now we have this function, and if it's well, whatever it is, it satisfies certain polynomial equation with coefficients in this algebra. hence f an equation namely the sum of ai f to the power I is 0, and let's consider this polynomial. So p of t is just this. Okay, and so these a's are polynomials. Okay, so again, we may assume, as we did before, that the lowest coefficient is not 0. Is not identically 0. And now let's consider the following auxiliary morphism. Pi tilde from x to a n plus 1, namely this pi tilde is our pi, and also this function f. Okay, so the last n plus first coordinate of our morphism pi tilde is just the function f. Pardon me? Auxiliary означает дополнительный.
По определению это вот ровно то, что...
Yeah, this is just the definition, and it's some English adjective meaning дополнительный. Okay. Now, pi was finite, and it implies that pi tilde is also finite. And we have pi of x lies inside the 0 set of p. So what do I mean by this? Well, this is just a polynomial in the extra variable, right? So the coordinates here are x1 and so on, xn, and the last coordinate is t. Okay, so just by the very construction, the image of x lies on this hypersurface, and the dimension of x, the dimension of this is also n, and this is n. So the dimension of x is n. Dimension of p equals 0 is also n, and we could choose this polynomial irreducible. Let's do this. And hence this will be irreducible, and hence the image of x is just exactly this. It's exactly this hypersurface. Okay. Now we have this hypersurface in x, and you can write it as the intersection of pre-image of P equals 0, the hypersurface in here, and the last coordinate T equals 0. Okay, but now since P equals 0 and T equals 0, only the lowest coefficient remains. Okay, and so this intersection is the same as the pre-image of A0 equals 0 hypersurface and just T equals 0. Okay. Okay. Because our well, here's our P. Everything is divisible by T, or else there remains the lowest coefficient A0. Okay. Okay. And so this means that the dimension of f equals 0 is the same as the dimension of A0 equals 0. And we assumed that this was at most n minus 2, right? And hence this is at most n minus 2. But this implies that A0 is a constant. But on the other hand, f divides A0, or sorry, f, no, A0 divides. Just from this equation, f divides, sorry, f divides A0, and hence f is also a constant. Well, f is invertible. Well, for polynomials, it's invertible. And f divides an invertible function, so f is also invertible. Okay? So far we only proved this lemma, and the time is through, I'm sorry. Next time we'll finish with the theorem, but essentially it's done. Okay? So, thank you for that. So sorry for the technical misfortunes. Yes?